closely at the device you are using to watch this video. If you break it down into its base parts, you are ultimately left with pieces of glass, metal, plastic, and just raw rocks and dirt. Yet somehow, these basic Earth materials can play movies and connect you to the rest of the planet. This happens because of a specific set of instructions that humanity has been refining for thousands of years. Today, we are going to follow that historical recipe to build a supercomputer from the ground up. To understand this, we have to look past the gadgets themselves. As the computer scientist Edgar W. Dijkstra observed, computer science is no more about computers than astronomy is about telescopes. Science is about how we use our tools to understand the world. Long ago, as human society grew more complex, people faced a practical problem. They needed to count crops, track local trades, and record numbers accurately, and their own brains were simply running out of capacity to hold all that information. The computer was created to solve this exact problem. It is a tool designed specifically to offload our mental labor. Building it has been humanity's longest, most complex DIY project. Before anyone could build a machine, humans had to invent a way to organize concepts. Ancient civilizations developed number systems, like the Hindu Arabic system we use today, which introduced revolutionary ideas like the digit 0. With numbers established, we get to step 1 of our build, the abacus. This photograph shows an early abacus, a wooden frame holding vertical rods with distinct rows of dark beads that slide up and down. The logic here is brilliant. You perform addition and multiplication purely by changing the physical position of those beads to represent different values. The abacus proved that abstract mathematical problems could be solved simply by sliding physical objects around in the real world. Moving beads by hand worked for centuries, but as global trade expanded, manual calculations became too slow and prone to human error. We needed automation, bringing us to step 2. Take a look at this device, known as Pascaline. Instead of fingers moving beads, a series of circular brass dials and gears drive the calculations automatically. However, the next major leap in computing didn't come from mathematicians. It actually came from the textile industry, with a device called the jacquard loom. This photograph shows the stack of stiff cards feeding into the loom's mechanism. The holes in these cards told the loom exactly which patterns to weave. It was a machine that could follow a set of saved instructions. Here is a portrait of Ada Lovelace, a mathematician who realized that if a machine could follow rules to weave yarn, it could follow rules to manipulate any logic, including music or art. By separating the physical machine from the instructions feeding into it, humanity established the blueprint for modern hardware and software. But mechanical gears are heavy, and they take time to rotate. To calculate faster, we had to replace physical movement with the speed of electricity. This brings us to step 3. This image displays glass vacuum tubes. These bulbs were used to control electronic signals, replacing the turning gears with the flow of light and electricity. As you can see in this photograph of the Mark I computer, these early electronic machines were massive. They took up entire rooms, consumed huge amounts of power, and generated extreme heat. Despite their size, they enabled a leap forward called the stored program concept. For the first time, both the data and the instructions on how to use that data were stored electronically in the same memory unit. We traded physical movement for electronic speed, resulting in autonomous machines that could execute long sequences of tasks without a human needing to turn a crank. Those room-sized computers had a problem. The vacuum tubes burned out constantly and took up entirely too much space. To solve this, we arrive at step 4. Here is an early transistor. It does the exact same job as a vacuum tube, but as you can see by its 3 small metal legs, it is tiny, solid, and runs cold. Engineers figured out how to cram numerous transistors onto a single piece of purified silicon. This image shows the resulting integrated circuits, small multi-pinned chips. This led to the microprocessor shown in this photo. By integrating thousands of transistors, we placed unbelievable calculation speed and memory onto a single chip, small enough for a personal desk. Look at this diagram. These tiny chips process information using ones and zeros at blinding speeds. But human beings type ones and zeros very slowly. To bridge that gap, we created translation layers. We developed programming languages, like Python, that let us write instructions using familiar English words, which the computer then rapidly translates into its own language. By shrinking the physical hardware and building language translators to communicate with it easily, we made computing cheap, fast, and accessible. This brings us to step 5. Because modern hardware is now microscopic and our coding languages are highly efficient, we can process data in volumes once considered impossible. Notice how this network grows and connects. Modern machines are designed to learn from information, recognize patterns, and make decisions that mimic the human brain. This stage combines several breakthroughs: machines that improve their own performance by reviewing past data, computers that understand human speech as we actually speak it, and a global web of remote processors that handle the heavy lifting from anywhere. By combining high-speed calculation with these massive datasets, machines have now moved beyond just following a single list of rules. They can now adjust their behavior based on what they find, acting less like a calculator and more like a collaborator helping you decide. Which brings us back to the present day and to that smartphone we started with. The device in your pocket represents the culmination of this entire history. It holds the positional logic of the abacus, the stored instructions of the loom, the electrical speed of the vacuum tube, and the microscopic scale of the transistor. Computer science is not about the glass and metal you are holding. It is about how you choose to use those layered ideas to solve a problem. Humanity spent 5,000 years building you the ultimate tool to offload your mental labor. The only question left is, what problem are you going to solve with it?